Students, from today's lecture, we are going to talk about the crystal structure of real materials. And we'll start from the most simple case, the crystal structure of metals. This table shows the crystal structure of some 16 typical metals. And for most metals, the crystal structure is mostly face-centered cubic structure, hexagonal closed-packed structure, or HCP structure, or body-centered cubic structure, or BCC structure. And we are first going to talk about three important concepts of crystal structures in metals. The first one is the number of atoms in the unit cell. The second one is the coordination number, which essentially is the number of the nearest neighbor items. And the third one is the atomic packing factor, which means the volume percentage of the items in the unit cell. So the first concept is the total number of items in each of the unit cells. So to calculate the total number of items n in the unit cell, you must count the number of items at particular positions in the unit cell. For example, this Ni is the item in the internal of your unit cell. So one internal item will count for one item in the unit cell. And this term Nf is the items at the face center of your unit cell. For example, in this FCC structure, this is your face-centered position item. And this item only contributes half item to this particular unit cell. So that you have to divide this Nf by a factor of 2 here to count the net number of items contributing to this unit cell. And similarly, if you have corner items like this, okay, you have corner item at this, each corner item is shared by 8 cubic cells. So you have to divide this number of corner positions by a factor of 8 here to calculate the total number of items in this unit cell. So in this way, you can do it. And this is your FCC, BCC, and HCP structures for your typical metals. And then you can calculate the total number of items in the unit cell based on the equations provided in the previous page. And the coordination number means the number of nearest neighbor items. And in FCC structure, the coordination number is 12. And in BCC structure, it is 8. And in HCP structure, it is again 12. So the atomic packing factor is defined by the volume of all the items in the unit cell divided by the total unit cell volume. So that's a definition. For example, if you have this face-centered cubic unit cell, you can calculate the total number, the total volume of items in the unit cell by doing this, right? The total number of items in the unit cell times the volume of each item, right? And divided by the total volume of your cell volume, right? So in this way, you can calculate the atomic packing factor for each of these unit cells. And in this way, here I just directly give the results here. For FCC structure, the total number of items in the unit cell is 4, coordination number 12, and then it's a homework practice. The atomic packing factor is 74%. And for BCC structure, the total number of items in the unit cell is 2, coordination number 8, and then the atomic packing factor is 68%. And for HCP structure, the geometry is relatively more complex. For HCP structure, you have this hexagonal type symmetry where you have essentially two lattice constant, which is C and A. C is your lattice constant in this direction. A is your lattice constant in this direction. So for HCP structure, you have a fixed C over A ratio of 1.633. And then the number of items in the unit cell is 6, coordination number of 12, and atomic packing factor is also 74%. The same or the identical with that of FCC structure. Essentially, you can see, or you will know that the FCC structure and HCP structures, they are correlated structures where you have the closely packed items in these structures. So like this. So this is actually an illustration of how the items are packed in these 3 atomic planes in the HCP structure. You can easily get these numbers from the geometry. So the next topic is how to calculate the density of a certain metal structure. To calculate the theoretical density of copper, you need to know the total number of items associated with each unit cell, the atomic weight, the volume of the unit cell, and Avogadro's number. Right? So it is described or calculated by this equation. So this is the definition, essentially the definition of your density calculation. And eventually you can come up with the theoretical density of copper in terms of its crystal structure and basic atomic nature. There are several important concepts I want to discuss regarding the crystal structure of metals. The first one is the solid solution. Okay, the solid solution. And in substitutional solid solutions, essentially you have 2 types of metal items, solute items and solvent items. And each of these items are occupying crystal lattice points. And so that you will have a combination of items in a single lattice or a single crystal structure. Another type of solid solution is so-called interstitial solid solution, where, because you have your interstitial sites in your crystal structure, for example, you have your octahedral interstitial sites in your BCC and FCC structures, and for certain combination of items, smaller items may occupy these tiny interstitial sites in your crystal lattice. So that's called interstitial solid solution. Typical examples include iron carbon, iron nitrogen, and so on. So another important concept is the single versus polycrystals. For single crystal, the periodic arrangement of items extends throughout the entire volume of the specimen without interruption. So essentially here you see a single crystal of some of the gems, and the single crystal is usually characterized by the small facets on its surface, which corresponds to certain crystallographic planes. And for polycrystals, it is the combination of a lot of single crystals together. For example, during typical processes of solidification and thin film deposition, you may have a lot of single crystals forming at the beginning, and when they touch each other, they form this so-called grain boundaries, where they just separate 2 parts of your single crystals having the same crystal structure but different orientations. So this is a polycrystal. So in today's lecture, we have studied the crystal structure of metals. Thank you very much.